Okay. So last time we discussed the actual deformations, right? This is okay. So this is, remember the assumptions. So the member still straight, and the cross sections also still remain the same in the same plane, okay, the perpendicular. Okay. Okay, now next is we can have this resultant force, okay, which we are going to imply all these stress resultants, right, like this review on yesterday. And then the next thing is, let's see our figure from the left, the middle, and the right. This is how distributed axial forces on each sections. So we have an axial loading, okay? And if you see that, we can imply the loading on, let's take some elements from this cross section and make it like a small, infinite small element, delta x, and we can say that if we want to make, in terms of functions, function of x, then we could also make a connections using mathematics or using calculus. Let's say that when we take the limit, okay, as the delta x going to be 0, then we could take this expressions, okay. Or we could say that the derivative of f with respect to x is negative px. Okay. Okay. P is the force that is going to be in this axial loads, okay, distributed on whole sections, and the F is the resultant. Okay. So this is axial force resultant. This is the axial force. Distributed on cross section. Okay, now let's make a space here before we take this. Okay, and then we can derive, or we can observe the stress, axial stress, as a function of x. We could write this f of x divided by a of x. So all with the terms x, which means that we are going to observe the delta, the delta x. And then we can also take the axial strain, and we take the axial strain based on this ux, okay, this ux here, this ux, the length, okay, with respect to x. So we are going to take the strain as a change in length with respect to x, or we could say that this will be du over dx. Okay, and we can also remember that in terms of the modulus, we can rewrite like that. So we can write also the strain in terms of modulus like that, and we can exchange this sigma with the F over A. Then the strain here comes, or let me write completely. So total elongations or we say the total elongation as a, so let me write du dx. So we take the integrations, with respect to dx. So take dx like that. So this will be a du. Then this will be, this should be u, but let me write the total elongation as e. So e is integrations, and let's assume the length is L. So we take the 0 until L to make this integrations logical. This becomes the axial force deformation equations. So this is an equations to determine how much the displacement, or how much the additional length, okay, if there is an axial force that deform the material. We can add another variable to make, let's say we are going to changing the length from u at 0 until some x. Let's say this is our e. Okay. Now we can express, or maybe not 0. This should be x and 0. Sorry. So then we can also express in terms of ux. This will be u0 plus the e. The e, we could apply the another variable. So we make this as a variable itself, x. Okay. So it will be a function at the end. So f. This is us. Or maybe let me just write with p. Okay. Okay. You can also express as this relations. Okay. So this is for general expressions. Okay, this is for general expressions. But most of the case, in our lecture, all of this we write in terms of function to make sure that it can be applied to any condition. But most of the case, the condition will be uniform. So we are taking the material as a uniform object. So we could make a simplification of our formula. So we say that this will be uniform axial deformation elements. Okay. What does it mean? It means that one, it has a constant cross-section area when they are deformed. And then secondly, constant Young's modulus, constant E. And then axial force applied only at the ends. And how to look at this uniform axial deformation? We could take as an example these two pictures on the left. Notice that there are some numbers 1, 2, 1, 2, 3, which means that all those elements, these members here, they are expected to have a deformation. Okay, they have expected to have an elongation. Okay. So you can imagine that it has some weight here. So this 1 and 2 on the left is going to take some elongation, so it will be longer when it's applied. So we can think that this weight here acts as a force, okay, as the axial force from here. Okay. So there will be some tensile here. Okay. Tensile here. And then this also applied similarly. So we take this, we have a rotation here, and we have a spring here. Okay. So we could see from this part or from this part that when it's going to move, imagine that if this is going to move to the left, the spring goes to the left, then there will be some interaction here, some reaction of the force here, that maybe this member 1, 2, 3, it will also getting elongated. Okay. So to simplify our formulations, we could rewrite the E. We can simply write first, let me write the condition that this is what we have. Now we can write down that the force is no longer we think as functions, but rather we just see the applied force at the end. And since the E also constant, we can also take that into our consideration in this formula. So we can see we can just see that the differences is on just the dx. So as long as we know the length of the members, then we can simply write our formula. Okay? Or we could just simply, if stated at the 0, then we could simply write that E F L A E. Okay. Now we can also rewrite this with another terms to give you idea how we can use this formula. So if, okay, let me write, if the small f is equal to L, AE, sometimes we can write the E as just F, basically the same formula. And then if we write that F is KE, K is like in the coefficient for us, if you remember this, the Hooke's law, usually we write with K. And in this case, our K is also A E over L. Okay, so basically the same thing. So the F, we can express this as elongation produced when unit force is applied. And K, or we can say that this is the flexibility constant. And then K is the force required to produce a unit elongation of the member. We call this case the stiffness coefficient or constant. Maybe coefficient is more suitable. I think if you remember the linear spring in Hooke's law in physics, we can also, it's applied similarly. It means that to elongate for some distance, we need this K to make out the force, right? So that's how we look at that. And this flexibility means how the member get stretched or get elongated with this force, okay? And how do we multiply that force to make some elongation? So it's basically the same. Okay, the key is just this E is fly. FLAE. Okay. You will see a lot later in the exercise. Okay, we'll skip some parts. There is actually sections for non-homogeneous member, but I will skip that part. Okay, we'll skip that part. That will be maybe in the later sections. So you now have the concept for the elongations, which means that based on what we have from previous chapter, the normal stress, strain, and of course the statics, then now if you have like a problem that is asking this displacement, the elongations, it means that first thing, check the statics, check the external force, and maybe if the question asking the internal force, also check the internal force by taking the same concept in the previous chapters. And then the additional questions will be the elongations, and you can pick up the E, okay, the formula for E. Okay, now the next is example. Let me give you example. Okay, this question here. Let me erase some part here. This is actually part of the answer. So let me explain later. What is that? So we have aluminum, I think, yeah. Aluminum. It's the 2014 T6 aluminum. I think quite common material for some structure. It has some modulus elasticity, 73.1 GPa. Let me read the questions. The question is, find the change in length of the bar looking at A with respect to E. So we are going to look at this and see that in every part of the bar there's applied force. Right? So maybe it's like from industry probably, that is like it's moving. So it's moved, goes here 4 kilonewton, 2 kilonewton, this part. Okay. This means it's not distributed loading. It's one side here force 3 kilonewton, one side here 3 kilonewton. So total is will be 6 for this. This will be 2 to the left. Okay. Now how do we see these questions? Okay. And the question given you the length for each bar. Okay. So A, B, B, C, C, B, and D, E. Okay. So they all have the each length, and then the bar itself has a diameter. So of course we will going to check the cross sections, right? So remember what we have before, the formula, the length or the elongations. We take the elongations as F, L, A, E, right? The force, I think the question given you the force. And in L, they all have the length, right? And E, they are the same material, which is the 73.1 GPa. The cross sections, they all have the same diameter. Okay. So I think as you focus on working on this formula, you can take one by one. Okay. It's quite, I think, quite straightforward, right? Now, if you would like, if you do like observations, let's say we have this member, okay, all this member, and the one that has elongation is just 1, 2, 3, right? Because it has this force going around. So if you want, we could cut each of the member and see how it's going on inside the member. Which means that if we take from A and then cut here, we have 4 to the left, which means we have total 8. Then we need to have a resultant 8 goes there, right? So in this member, let's say we have the force here, 8. So we take 8 going over there. Let's just say there will be 8, or maybe inside here. 8 kilonewton. Okay. And then what about if we cut this? Or maybe if we want to make, oh yeah, no matter, doesn't matter. So 8 going from that resultant, and then another one will be 4 kilonewton, right? So 6, 6, 4, 10, 8, 2. So this will be going there, this will be going there, right? So this will be 2 kilonewton, this will be 4 kilonewton. Well, you could check one by one if you would like. So 8 goes there, from here, huh? Okay. If you want to maybe include 8 and 6 and 4, so 4, 6, 10, let me check, 8, 2, so 8 goes there, 6, 6, 2, it's 4, right? 6, 2 is 4, 4 need to be with 4 to make it 0, so I think it's correct, right? It's equilibrium, right? If you check one by one, so it's 2 going there. This is 6, right? So 6 and 2 is going to be it's going to be 8, and those will be 4, 4. Yeah, I think that should be okay. Okay, now we could apply the formula. So we are going to take the elongation total is elongation for AB plus elongation for BC plus elongation for CD. Okay. So only 3 member, because the last member is there will be nothing there, right? Okay, and then we move to the calculations, all in kilonewton, so it's 8,000. Let me write in newton, so 8,000 newton, and then what is the length is 4 meter. Let me write in millimeter, so the expectations will be in millimeter because the diameter is in millimeter, and then divide pi and then 25 squared, right? And then millimeter squared, and then the E is 73.1, so 73/100 for MPa or Newton over millimeter square. So we can cancel all nicely. and then plus 4,000 Newton, 2,000 millimeter, and then again the same here also. That I think we can factorize later. I'll just write first. It should be written in the formula, but I'm directly right here. And it's not plus here because as we see, this is going to be oh wait. I think it should be wrong directions, right? Should be in tensile here, sorry. So 6, 2, this is going to be there. So this is tensile, and compressive. So plus and then minus the 2,000 Newton, 2,000 millimeter. So we could take the 1 over so let's cancel all these things first. Okay. Now we have 73, 100, and then maybe taking 1 million. Can we do that? 32 plus 8 plus minus 4. So it will be 36. Maybe if I'm not mistaken, previously I calculate this is around 0.25, but maybe this is wrong. We can check later in calculators. But this is how it is. Okay. Okay, I think one more example. Let's see. This is, let me write the, this is for statically. Maybe let me write in a new page. So we name this as statically determinate structures. So what we need to take, okay, equilibrium. This is the summary from the previous example. So the equilibrium, the element force deformation behavior, and geometry of deformation. Okay, I forgot to pick up the question here. Let me draw. Okay. Now let's say this is the member 1 and member 2. Diameter is 20 millimeter. Diameter 2 is 15 millimeter. This is 300 millimeter. And this is 200 millimeter. I think I draw too small, but I think that's okay. And then it has applied force 10 kilonewton. And another force here, which is 30 kilonewton. Okay. And we have E1 is 200 GPa and E2 is 70 GPa. Yeah, we should have this first before the previous example, but let me just this as a review. Okay, as a review. So a typical element, when we solving this member or elongation at the member problem, so we could think a member that will have applied force on the each ends. Let me just write as Fi, and then it will have the length, and of course it has the cross sections, it has the E, right? So as long as to work on for all the problems, the axial force, as long as you know the force, you know the length, you know the cross sections, you know the modulus, elasticity, you could apply the elongation formula. Okay. It means that first check the equilibrium for each member. Okay, how does it look like, and then the behavior and the geometry. Okay. Now, if you look at the free body diagram. Okay, so first, actually what we did before is actually we cut, let's cut from here, cut here, and then we see that we have a reactions for 10 kilonewton, which is the F2, and then we cut on this part in one. We have a reaction here. Okay, so we are going to have F1 will be 20, right? But it's to the left, so we can write that as a negative 20. So F1 F1 plus 30 kilonewton is equal 10 kilonewton. So F1 is negative 20 and F2 is this 10 kilonewton. Okay, remember that we can write the E as F, or we can write directly F, L, A, E, right? So if we consider just to look at just the small f, then we could take the F1, L1 over A1, E1, and F2. Okay, now we get this. Okay, you can write the calculation if you want. And we can get E1 and E2 from this point of view, which means the 1 will be negative, right? It will be negative. It means that it is not a tensile, it's a compressive. So the length will be minus, okay? The length will be minus. And then we could take so this is for this is what we call, this is the equilibrium part. This is the element force deformation, which means we are going to calculate the E. And then for the geometry, we are going to apply what we call as compatibility equations. I think this will be next week's subject, focus on this compatibility equations. So we can write down some equations that relates this to E. Okay, so we could write UC is E1 plus E2. Okay, I think we are going to complete this next Tuesday. Okay. And for the quiz, please just keep update on Moodle. I will give you maybe 3 days just to complete. Okay. So you can choose which day you are going to take. Okay. I think we'll be start from this maybe from this afternoon maybe. You can check, but you can take time. You can check tonight or late tomorrow.